Okay, 2.4. In 2.4, we're going to learn about the product rule and the quotient rule, which are two of the big three rules remaining for derivatives in our class. But before I get into the product and the quotient rule, I don't want the importance of 2.3 to be lost upon you. We learned a ton of information in 2.3, and without that information, you really won't be able to do anything in any section for the rest of Chapter 2. So let me review that real quick. We started 2.3 by learning these big three rules: the power rule, the coefficient rule, and the sum rule. The power rule just tells you, for example, that the derivative of, x to the third power is equal to 3 times x squared. Loosely speaking, you bring the exponent down in front, and your new exponent is 1 less than it used to be, if that helps any. And then we tacked onto that rule the coefficient rule, which says if you're not just taking the derivative of x cubed, but you're taking the derivative of, 5x cubed maybe, all you have to do is leave that 5 alone and multiply that by the derivative of x cubed. So it'd be 5 times 3x squared. In other words, 15x squared. You pull constant multiples out in front of your derivative symbol. This a goes out here. And then finally, we added the sum and difference rule, which is a really nice rule. It says if you're figuring out the derivative of, not just x cubed, but x cubed plus x to the 10th power, for example. All you got to do is figure out the derivative of x cubed, so that's 3x squared using our power rule, and then add to that the derivative of x to the 10th, which is 10x to the 9th using our power rule. And the derivative of that sum will just be the sum of those two derivatives, 3x squared plus 10x to the 9th power. Those rules are awesome, and with those three rules, we can almost take the derivative of any polynomial. Although if you're kind of nitpicky, you might not like using the power rule when the power is just equal to 1, x to the first power. So instead of using the power rule there, you can just kind of memorize that the derivative of your variable x is just equal to 1. And similarly, you can just kind of memorize that the derivative of any constant is just equal to 0. And don't confuse this constant rule with this coefficient rule. Constants are treated differently when they're being multiplied by a function like 10x squared, as opposed to all by themselves like the derivative of 10. And I thought that that was plenty of information for one section and kind of overwhelming, but your book did not. Your book thought it was a good idea to tack on 2 more rules, the exponential rule and the logarithmic rule, which I did at the very end of the section and didn't put on any of the homework. And the idea there is if you're taking the derivative of any exponential function, like 3 to the x power, your answer for the derivative is almost just 3 to the x power. You just have to remember to multiply that thing by the natural log of 3. So the derivative of 3 to the x would be equal to 3 to the x times the natural log of 3. And a nice consequence of that rule is, because the natural log of e is just equal to 1, the derivative of e to the x would be e to the x times the natural log of e, which is e to the x times 1, which is just e to the x. Most students, if I'm being perfectly honest, memorize this as kind of a different rule, but really it's a consequence of this kind of more general rule up above. And along the same lines, we have this general rule for the derivative of logarithmic functions. So if you're taking the derivative of, the log base 5 of x, your answer would be almost 1 over x. You just have to remember to tack on this natural log of 5. Note that up here, we have to take the base and multiply by the natural log of that base. Whereas down here, we have to take the base and divide by the natural log of that base. There's a lot of similarities between exponential functions and logarithmic functions. And for that reason, there's a lot of similarities between the derivatives of exponential and logarithmic functions. So if you're asked to figure out the log base 5 of x, your answer would be 1 over x times the natural log of 5. And a nice consequence of that rule, again, because the natural log of e is just equal to 1, is if you're taking the derivative of the natural log of x, the natural log of x is just asking you the log base e of x. Using this rule, we'd say our derivative is 1 over x times the natural log of e. But again, the natural log of e is just 1. So the derivative of natural log of x is 1 over x times 1, or 1 over x. Again, this down here is really just a special case of this more general rule up here, but most students memorize it as a separate rule. When you see natural log of x, you get happy because the derivative is so easy, it's just 1 over x. Anyways, those were all the pieces that we learned back in 2.3. But this ain't 2.3. This is 2.4, where we're going to learn some new rules. We're going to use all these different pieces inside these things called the product and quotient rules. All those rules that you just learned are often referred to as building block rules. They're kind of the pieces that we will need going forward. But think about if you were asked to find the derivative of x squared times the natural log of x. Right? You might be like, well, this is easy. I know the derivative of x squared using my power rule is 2 to the x power. And I know the derivative of natural log of x, that was that one you tacked on at the end of the video last time. It's 1 divided by x times the natural log of e, or just 1 over x. And you're like, so clearly the derivative of x squared times the natural log of x should be equal to 2x times 1 over x, I guess, right? The derivative of this times this feels like it should be this times this, but it's not. It's a very common mistake, so much so that I don't even like leaving this on my notes right here. I want to make this really clear that this is not the case. The derivative of a sum of two functions is the sum of the derivatives, but the derivative of a product of two functions is not the product of the derivatives. Why not? Well, let me show you a quick counterexample, maybe proving it to you. Suppose somebody asked you to take the derivative of x squared. Right? You know what the derivative of x squared is. It's just 2x. But think about somebody else who was like, wait a minute, x squared, isn't that just x times x? And you'd be like, yeah, for sure. And isn't the derivative of x just equal to 1? Well, yeah. So shouldn't the derivative of x times x be the derivative of x, which is 1, times the derivative of x, which is also 1? Shouldn't the derivative of x squared, by this logic, just be equal to 1? And if you were really paying attention, you'd be like, well, it would be, except that the derivative of a product is not equal to the product of the derivatives. Here's where things fell apart right here. X squared is x times x, but the derivative of x times x is not the derivative of x times the derivative of x. I do this a lot. Like I go on these big rants talking about what you should not do. Maybe I shouldn't do that. Maybe I should focus more on what you should do. What should you do? You should use what's called the product rule. And the product rule is laid out for you in our standard notation right here, but it's really overwhelming to look at. What it's saying is the derivative of a product of two functions, so think like x squared times the natural log of x, is the derivative of the first function, so the derivative of x squared, times the second function. No derivative here. This is just taking the derivative of the f, not including the g right here. I'm going to multiply the derivative of the first function times the second function. Then I'm going to add to that the derivative of the second function times the first function. No derivative here or here. The derivative of a product of two things, big parentheses to try to make this really clear, is the derivative of the first thing times the second thing plus the derivative of the second thing times the first thing. It's a lot easier to say than it is to write with this notation. So often we use shorthand notation. I think you're going to like this one a lot better. If we use these little primes to represent derivative, which kind of makes sense because we've been writing like f prime of x, then this is saying the derivative of f times g, where f and g are both assumed to be functions, is f prime, the derivative of f, times g, no derivative, plus g prime, the derivative of g, times f, no derivative. So if you were asked to figure out the derivative of x squared times the natural log of x, you would absolutely not say that it's 2x times 1 over x. What you would instead do is be like, all right, I got to take the derivative of the first thing, there's the 2x, then I got to leave the second thing alone, natural log of x. Then I have to add to that the derivative of the second thing, the derivative of natural log of x is 1 over x, times leave the first thing alone, x squared. Using the product rule, the derivative of x squared natural log of x is 2x natural log of x plus 1 over x times x squared. You can make this a little bit prettier if you feel the need, right? 1 over x times x squared. I can cancel an x from the top and an x from the bottom, and I'm left with just an x. Now, I think this is a little bit prettier than this. And if you're really into rewriting things algebraically, I suppose you could factor out this x and be left with 2 times the natural log of x plus 1. But whatever, I don't care too much about that. I'm just trying to demonstrate different ways you can write your answer. I would be more than happy if you could get this far, or really even this far. This is a business calculus class, right? I don't have to prove every result to you. I can ask you to just believe me because I'm your teacher that this really is how you take the derivative of products. That this isn't just some craziness that I made up to mess with you guys. It really is true that the derivative of a product of things is the derivative of the first thing times the second thing plus the derivative of the second thing times the first thing. Google it if you don't believe me. But as is often the case, I feel a little bit guilty just asking you to trust me. So maybe I can give you a little picture proof, just showing you where this comes from, just in case you're interested. I promise I won't take too long. Let this length right here represent the value of some function f. When we're taking derivatives, we're really interested in the rate of change. So think about this is the value of some function f at some point, and then a split second later, maybe this is a little bit bigger. So originally f goes from here to here, and then a split second later, it's a little bit bigger. That tiny little difference here, how much the length of this line is kind of changing by, represents f prime. Right, it's the change in the length of this green line. It was this, and then a split second later, it goes all the way from here to here. So the change is this tiny amount right here. I know that doesn't make any sense, but stick with me. Let's picture some other function and let's draw it in this direction. And we'll call this g. And the length of this line represents the function g at some instant. And then a split second later, it's a little bit longer because this function is changing. The amount that it changes by, I can kind of picture as g prime. So here's my function, here's f prime, here's another function, here's g prime. Think about what it means to take the derivative of a product of two functions, right? If f is this long and g is this long, then f times g is the area of this rectangle right here, right? If you're in a room and this wall is 8 feet long and this wall is 10 feet long, the area of your room is 80 square feet, the 8 times the 10. So at some instant, f times g is the area of this red rectangle. And then a split second later, because f is changing and g is changing, I end up with this much area. How much has my area changed by? Well, it's changed by kind of all of this stuff in purple here. How much is that stuff in purple? Well, here's kind of a bad geometric argument for how big that is. First, let's think about this rectangle, this brown stuff. The area of this stuff in brown is, well, it's a rectangle, so I can just do the base times the height. It's f, this length, times g prime, this length. But that's just one little bit of the overall change. I still have to account for all this stuff. Well, think about this little rectangle down here in pink. How big is this guy? Well, it's g, this length, times f prime, this length. Here's where my analogy falls apart. You might be like, oh, you're forgetting this tiny little square right here. Yeah, this ends up being equal to 0 because of some properties of limits. You might think that it should be f prime times g prime, but it's not, for some complicated reasons that deal with infinities. But if you don't worry about that, you can kind of see that how much this picture changed by was more or less f prime g plus g prime f, the brown area plus the pink area. That make any sense? Probably not. Whatever, you don't need to know it. It's a business calculus class. Let's move on. Before I do another example, I want to remind you of something. Sometimes we don't just want the derivative of a function. Sometimes we want to evaluate that derivative. Maybe instead of saying take the derivative of x squared natural log of x, I said some function f of x is x squared natural log of x, and I asked you to figure out f prime of 1. If my function is x squared natural log of x, then the derivative using the product rule is just the derivative of the x squared times the natural log of x plus the derivative of the natural log of x times the x squared. And the derivative of x squared is 2x. So I take that 2x times the natural log of x and then add to that the derivative of natural log of x, which is 1 over x times x squared. And I get the same result that I came up with before, that f prime of x is 2x natural log of x plus x when I simplify this part. But maybe it's not asking for f prime of x, it's asking for f prime of 1. Just a little reminder that once you have f prime of x, figuring out f prime of 1 is super easy. All you got to do is copy this blueprint right here, changing all the x's into 1s. So it's 2 times 1 times the natural log of 1 plus 1. You may or may not remember that the natural log of 1 is defined to be equal to 0, because the natural log of 1 is asking you the question, what power do you got to raise e up to make it equal to 1? And e to the 0 power is 1, because any number to the 0 power is 1 other than 0. So the natural log of 1 is just 0. I get 2 times 1 times 0, or just 0 plus 1. F prime of 1 would be equal to 1. This isn't anything new with the product rule. It's just something I want to remind you of, because I know on the homework, sometimes they ask for f prime of x, which is typically what I demonstrate how to do in these videos. But sometimes they ask you to do f prime of 1, which really just means figure out f prime of x and then change all the x's into 1s. But because I so seldom demonstrate this in the videos, I want to make sure that I did it at least one more time. So there it is. Let's get back to the product rule. Do you remember this problem? I think it was in the last section where I asked you to take the derivative of 2x plus 1 squared. And I was like, we can't do it. It's too hard. But what we could do is take 2x plus 1 squared and expand that binomial. So think about it like 2x plus 1 times 2x plus 1. And then do some FOIL to get 4x squared plus 4x plus 1. And then take the derivative of this using our different rules. Right? We had to do all this algebra so that we could use our rules, because we didn't have the ability to take the derivative of a product at that point. Now we do. If somebody asks you to take the derivative of 2x plus 1 squared, Just think about when you square something, you're multiplying it by itself. So really that person is asking you, what's the derivative of 2x plus 1 times 2x plus 1? Yeah, you could use FOIL, but you don't have to because we can take this derivative now. Think about this is f and this is g. The derivative of a product is the derivative of the first thing, so this 2x plus 1, times the second thing, this 2x plus 1, plus the derivative of the second thing, this 2x plus 1, times the first thing, that 2x plus 1. The derivative of 2x plus 1 is the derivative of 2x plus the derivative of 1. We pull the 2 out in front. The derivative of x is equal to 1. What I'm saying is this whole thing right here, its derivative is just equal to 2. We don't take the derivative here. There's no d over dx symbol out in front of it, so I'll just leave that 2x plus 1 alone. Now I take the derivative of this 2x plus 1. The derivative of this 2x plus 1 is again just equal to 2. And then I don't take the derivative over here, so I get again 2x plus 1. I got 2 of these 2x plus 1s plus 2 more of these 2x plus 1s. So I got 4 of these 2x plus 1s. Or if you really don't like parentheses, distribute the 4 through and you get 8x plus 4, which is the exact same answer we got before when we took the derivative of this thing. Maybe you can see the 8x plus 4 over here. You could argue that that didn't save us a whole lot of time. It was almost just as easy in this specific example to expand the polynomials. Yeah, it was, but what if instead of 2x plus 1 times 2x plus 1, somebody asked you to figure out the derivative of x cubed plus 3x squared plus 5x plus 7 times 2x plus 1? To expand this out would be a nightmare. To multiply this 2x times each of these 4 terms, multiply this 1 by each of these 4 terms, collect like terms, that would be miserable. You would hate doing that. But you can use the product rule pretty easily. Take the derivative of this, multiply it by this, add to that the derivative of this, multiplied by this, and you're done. I'll leave that as an exercise for you if you want to do it. One more comment I want to make. Just like we could have used the product rule up here, we really could have used the product rule down here, but I don't recommend you do. Let me show you how that works. If somebody asked you to take the derivative of 3x to the 5th and you were thinking very literally, you could be like, well, this is 3 times x to the 5th power, right? I'd be like, yep. So then couldn't I use the product rule and say that this is equal to the derivative of 3 times x to the 5th power plus the derivative of x to the 5th power times 3? And I'd be like, yeah, absolutely you could. And then they'd be like, all right, cool. Because the derivative of 3, let's see, this is a constant. I know that the derivative of any constant is just equal to 0. So when I'm taking the derivative of this 3, I get 0 times x to the 5th power plus the derivative of x to the 5th power, which is 5x to the 4th times 3. And I'd be like, yeah, that's exactly right. But look what happens. 0 times anything is 0. So this whole term just goes away. I get 0 plus 5x to the 4th times 3, 15x to the 4th. There's no reason to use the product rule when one of the two things in the product is just a constant. Because what ends up happening is the half of the product rule that takes the derivative of that constant just goes away. It'll always turn into 0. And then the other half of the product rule will leave the constant alone and multiply that by the derivative of the function, the x to the 5th. Essentially, this half of the product rule acts like the coefficient rule, where you don't take the derivative of the coefficient, the 3, you bring it out in front if you want, and just multiply that by the derivative of x to the 5th. The point that I'm trying to make is the product rule is consistent with the rules that we've learned so far, and you could use it instead of the coefficient rule if you really wanted to, but don't bother. This takes longer than just pulling the 3 out in front and taking the derivative of x to the 5th. At the start of this video, I mentioned that there's 2 different rules, the product rule and the quotient rule. I think this is a good time to stop, devote this video just to the product rule, and save the quotient rule for the next one.